everyone. I'm Lady Parker, and this is Group 29. And our presentation is titled Transient Response Analysis on a Second Order Feedback System in Control System. So, in control system, a transient response describes how a system behaves immediately after an input is applied. Immediately after an input is applied before it reaches the steady state. And understanding this is very important because it helps engineers evaluate whether a system is stable, fast, and accurate. Yes. So in this presentation, we will analyze a feedback control system and determine some important performance parameters.
A question. So the transient, before we even start, the transient response analysis is very important in a control system design. It allows the engineer to study how the system reacts during a transition period before reaching the steady operation. In most real world cases, like robotics and electrical circuits and some mechanical control systems, uh, it exhibits the transition behavior when subjected to inputs. So, the main objective today is to analyze the control system and find the natural frequency, damping ratio, and the maximum ratio. And to obtain these parameters, we begin with the open loop transfer function. We analyze the system using standard.
Jackson from Group 29. I'm presenting on the unity feedback system and characteristic equation. So in the system, we consider a unity feedback control system to analyze the system stability. We use the characteristic equation 1 plus g of x equals 0, where g of x is the open loop transfer function. To simplify the equation, we simplify both sides by the denominator. S bracket open s plus 2 bracket close multiplying s plus 6 bracket close. This leads to the characteristic equation s bracket open s plus 2 bracket close bracket open s plus 6 plus k equals 0. Now we expand the equation to obtain the polynomial form that can be used to determine the system force. Thank you.
So please, my name is Theophilus Champon and I'm from Group 29. So at this point, I'm going to help expand the equation. So first we multiply s plus 2, s plus 6 here. So when we multiply them, we get s squared plus 8, s plus 12. Then we multiply it with the x that was here. So multiplying with the s, we are going to get s cubed plus 8s squared plus 12s plus k is equal to 0. Then now our gain, which is k, is equal to 10. So when gain is equal to 10, then we are getting s cubed plus 8s squared plus 12s plus 10 is equal to 0. Now, using a calculator to solve for the solutions of the equation, we are going to get the first solution going to be equal to negative 6.36s. The next solution being a complex solution, we are going to get negative 0.8197 plus or minus j 0.9488s. So now, the complex pools are very important. This is because they determine the oscillatory behavior of the system. Now, as I said, we take the complex parts and our parts become 0.8197. Then the imaginary part, which is mu d, becomes omega d becomes 0.9488. Thank you.
Where by comparing what they had with the standard second order code, which is this. Yeah, so after everything they had the real part, which is sigma to be equal to 0.8197, and the imaginary part, which is omega d, being equal to 0.9488. So now we move on to find the natural frequency and the damping ratio. So the natural frequency's formula is equal to the square root of sigma squared plus omega d squared. So then we substitute the values to get square root of 0.8197 squared plus 0.94882 squared, which will give us 1.25 rad per second, and that will be our natural frequency. Then we use the natural frequency, which is 1.25 rad, and the sigma value, which is a real value, which is 0.8197 squared, to find theta, which is our damping ratio. So theta is equal to sigma over omega d. Then after substituting the values, we have theta to be equal to 0.65. Finally,
From our calculations, the natural frequency omega n of the system is now approximately 1.25 rad per second. This tells us how quickly the system tends to oscillate. The damping ratio now tends to be approximately 0.65. The damping ratio shows how quickly oscillations decay. A value between 0.5 and 1 indicates a well-damped system. Next, we calculate the maximum overshoot, which measures how much the response exceeds the desired output before settling. The formula for the maximum overshoot is what we have here, which is the e raised to the power negative pi times the damping ratio all over root of 1 minus damping ratio squared. So substituting the damping ratio into it, which is 0.65, we get our maximum overshoot to be approximately 6.8%. This means that the system only exceeds the target value by a small amount before stabilizing.
Well, no, Melchizedek from computer engineering theory, and I'll continue from my group member in there. To summarize our results, the key parameters obtained from the analysis are natural frequency, which is equal to 1.25 rad per second, damping ratio, which is equal to 0.65, and the maximum overshoot, which is equal to 6.6%. The natural frequency indicates that the system is stable and well damped. The natural frequency shows that the system responds to a moderate speed. The damping ratio of 0.65 means oscillation reduce quickly. The maximum overshoot of about 6.6% shows that the system does not exceed the desired output significantly. In conclusion, the system demonstrates stable behavior with minimal oscillation and acceptable transient response, making it suitable for practical control system applications. Thank you.